Okay, we are right back at it on Redox number 3. Now, as I mentioned in the previous video, if you had a chance to watch it, what's coming up in a couple of weeks, or actually maybe next week, depending on when you're watching this video, is a 2-part lab, where part 1, you're doing what's called a standardization, which means you are determining the molarity of a solution to a very precise degree. And you probably will have talked about molarity in lecture by now, but we'll do it in lab if we need to, which is the moles per liter. So the idea is to standardize a solution week 1. Use that solution in week 2 to actually do something useful. In this case, what we're looking for is the mass percent of sodium hypochlorite in bleach. It should be around 5%. That's typically what bleach is. So after 2 weeks of doing lab, 2 weeks of doing calculations, your final answer should be somewhere around 5%. Now, I'm not going through all the calculations here because it involves molarity calculations, it involves titration calculations where you have to do mole to mole conversions using, and all those stoichiometry things that you've learned in lecture. So I'm not doing the stoichiometry. All I'm going to focus on is on balancing an equation that's similar to the 2 equations you'll balance in this lab, but you'll read and get there. So this one's a little more challenging to balance, but I'm not going to do those for you. I'm going to do one that's similar. So all of these analyses fall under the heading of iodometric analysis. Well, that means using iodine to measure something or to analyze something. So what I'm going to show you, instead of hypochlorite, is actually another ion. Very common ion to look at in something like wastewater or something like that. So this is similar, but not exactly the same. So here's the deal. So we have to make some assumptions here. Well, we're going to do this in acid. I'm never going to do any of these in base. I'm going to let you figure out how to do the reactions in base. Fine. And we're going to do something a little different. So let's assume that acetic acid So we're going to assume that acetic acid is our acid. So when we say in acid, excuse me, instead of just saying H+, it's acetic acid. Fine, okay? And instead of using sodium ions and any other counter ions that we need, I think the only ones we need are, let's use potassium this time. And we'll stick with chloride. It doesn't really matter. Chloride is probably the most common one to use. Great. So acetic acid, you have as much of this and as much water as you want. You have as many potassium and chloride spectator ions as you want. I think I can probably fit this in up here. Let's give it a shot. So here's the generic reaction. So it would be potassium chlorate, because you have to have a counter ion to the chlorate, plus potassium iodide, plus acetic acid. Oh, some students asked in class last week, why do we write it this way rather than C2H4O2? That's because this is the hydrogen that is deprotonated, the one that produces the H+. So this is a monoprotic acid. It's a monoprotic weak acid if you want to be precise about it, but this is where the H+ comes from. Fine. And this forms iodine plus KCl. All right, so we want to break this down. So the first thing I think you can do here is get rid of the spectator ions. Well, I think we can figure out what's happening here. So we have chlorate is turning into chloride, and potassium there is the spectator ion. So we can probably safely just get rid of that. We'll put it back in later. So we have chlorate going to chloride. Let's just go ahead and balance it now. Oh, that's negative. Because we know the spectators aren't reacting. We'll put them back in at the end. All right, let's see. So the chloride's balanced, so we have to put 3 waters over here, and then 6 protons there. Total charge on this side is positive 5. Total charge over here is negative 1. So what do we have to do? I think we have to use negative charge. So I think we have to put 6 electrons here. If I make a mistake, we'll just go back and correct it. That's okay. So what reaction is this? I guess this is reduction. That's fine. Okay. Now the acid is there just to make the reaction happen, so we don't really worry about that right now. So the other reaction is iodide reacting to produce iodine. Again, ignoring the potassium spectator for now, ignoring the acid for now. Okay, so we have to put a 2 here. And if I did it right, we better put electrons on the other side. That would really be screwy if we didn't. So we put 2 electrons there. 2 negative charges, 2 negative total, we're good to go. And that better be oxidation. If it isn't, then I messed something up. Great. Now we have to add them together. Pretty straightforward. So we have to multiply this one by 3. Least common multiple. So 6 electrons. We have to make that 6 and boost everything else up. And I'm just going to rewrite everything. So we go from redox, oxidation, then to the overall redox reaction. So we're going to have, and the electrons cancel, so I'm not going to worry about those. So we'll have chlorate plus 2 iodide plus 6 protons, and that produces, keep going in order, made a mistake, didn't I? Forgot to carry the 3. Yep. Gotta catch that stuff. Okay. Goes to 3 I2 plus chloride plus 3 water. Since I already made one mistake, let me make sure I've got it. So chloride, we just bring that down. Just bring that down. 6. I think we got everything there. Great. 3, 1. Okay, I think we're good to go, but let's just double check it. Make sure we have it. 1 chloride, 3 oxygens, 6 iodines, 6 iodines. Okay, good. Now, with the spectators, all we're doing is putting them back in. And then the acid. Okay. It all looks right. Ran out of space. And then, of course, I now messed it up because I put the acetate ion back in there. I put 6 acetate ions back in. Well, now what do? Well, that's kind of wacky. So I guess I have to put in plus 6 potassium acetates. And it should work because the potassium is better balanced. So we have 1 plus 6 potassiums is 7 potassiums. 1 plus 6 more is 7, that better work. And then 6 acetate ions. So I think we're good to go on this one. That's the kind of one you're going to do in the lab. So you'll be given 2 equations on week 1 of this lab and 2 equations on week 2 of the lab. Read carefully, one of them's the same. So it's actually 3 different redox reactions. You'll want to strip out the spectators, ignore, if you will, the acid, balance it like you always do, rebuild in the spectator ions and the acid, and then add any ionic compounds involving the anion of the acid on the other side, so that it comes out to be everything's represented as a neutral species, which is much more realistic for the lab. And then you'll need the coefficients. In this case, it'll be a 1 to 6 to 6 to 3 to 1 to 3 to 6 ratio, and then you can do your stoichiometry from there. And that's all she wrote.